we're going to look at a couple of tests that we can use to determine if series converge. First is the integral test, and then we'll look at the comparison test as well. To do the integral test, what we need to do is we need to have a continuous function that agrees with the series, or the sequence that is, at the positive integers. What do I mean by agrees with? Well, the function value at the positive integers has to be equal to the sequence values. It turns out then that the series will converge exactly when the integral converges. So if the series converges, the integral converges. If the integral converges, the series converges. And the same could be said for divergence. If the integral diverges, the series diverges, and vice versa. Over here we have a little graphical demonstration of why this works. The rectangles here represent the terms of the series, and this shows why if the series converges, so does the integral. This rectangle has an area equal to the first term of the series, or the sequence. The second term, or the second rectangle is the second term, and so on. Because the area under the curve is less than the area under the rectangles, if the area under the rectangles converges, so does the area under the integral. Down here, we have a demonstration that if the integral converges, so does the series. Now, you might think for a moment that we're cheating here. Here we have the integral, or not the integral, but the curve that we're going to integrate. Let's pretend it converges. Well, if it converges, then the rectangles that are below it, the sum of the areas there, would also converge. Now the sum here, this is actually a sub 2. This first rectangle has areas a sub 2 plus a sub 3 plus a sub 4 and so on. So that series would converge. Well, if the series from 2 to infinity converges and a sub 1 is just a number, then when we add that back in, it will also converge. Let's see this thing in action. We're going to use the integral test to determine if this series, n over the quantity 2n squared minus 1 to the 3 halves, converges. We're going to use this. So the one thing that we need to have is that our function needs to be decreasing. Our function, if you graph x over 2x squared minus 1, it's decreasing. And notice, how did I get x over this quantity? I just replaced all the n's in my series by x's. Now I take this integral. This one's nice to deal with because the denominator's derivative, well, that is 2x squared minus 1's derivative, involves x, and so we use substitution. So we'll let u be that x squared minus 2x squared minus 1, du is 4x dx, solving for x dx because that's what our numerator is, we get 1/4 du. So we write this as an improper integral, doing the limits. T is going to approach infinity. We're going to go from 1 to 1/4. We're going to go from 1 to t. Now that's again in x. X goes from 1 to x equals t. And then we make our substitution. Now, in this step, we're pretty good at integration, so I'm free to skip a couple steps, but we're going to take the negative 3 halves, add 1. We end up with negative 1/2. We have to divide by negative 1/2, which is equivalent to multiplying by 2, which is over here. And it should be u to the negative 1/2, but since u is equal to 2x squared minus 1, I can go ahead and substitute that back in. Now we calculate, plug t in. We still need to evaluate the limit. But we end up with this fraction, 1/2, and then we have the radical 2t squared minus 1 in the denominator. But this term goes to 0 as t goes to infinity. This term is equal to 1/2, so it's just 1/2. We determine that the integral converges, and so then does the series. The second test we're going to talk about is what's known as the comparison test. We're going to take series that we know converge or diverge and use them to determine if our series that we're looking at is convergent or divergent. Before we do that, we need to know, hey, what series do converge? We had a result with integration, and we could use the integral test to prove that this series, 1 over n to the power p, is going to converge when p is greater than 1 and diverge whenever p is less than or equal to 1. So we'll use that as we go. And how does the comparison test work? So we have two series, sum of a sub n and the sum of b sub n. These have positive terms. If b sub n is convergent and a sub n is less than or equal to b sub n. Well, if that's true, then what would end up happening if I replace the b sub n's, I get smaller values overall, and so a sub n will also be convergent. On the other hand, if b sub n is divergent, and we end up picking a sequence that's larger than b sub n, at least on some of the terms, well, since b sub n diverges and we're taking out something larger, we're going to end up with a divergent sequence. See how this works. We want to determine if this sum, so the numerator n plus 2, the denominator is the square root of n cubed plus 4, does that converge? Here's how we get a rough estimate. The numerator, in the long run, will behave a lot like n, and that 2 will have very little influence. In the denominator, it's the n cubed that's doing all the action. We drop off the 4 just to get a sense for how this thing grows. So we end up with n over n cubed, square root of n cubed, just by taking the highest powers of n in the numerator and denominator. Well, n cubed, or square root of n cubed, is the same as n to the 3 halves. N divided by n to the 3 halves, it simplifies to 1 over n to the 1 half. We look at the exponent. We're going to take the sum of this type of thing, the exponent's 1 half, and by the p-series test, we know that this sequence, or the series with this, would diverge. Okay, so our goal is to show that the series, the sequence we're looking at, is greater than, I should say greater than or equal to, some constant multiple of this quantity, 1 over essentially the square root of n. Now, why do I do a constant multiple? Well, the constant multiple is not going to affect whether or not my series converges. And I think it diverges because this guy diverges, so we need to make sure that this is larger than what we're playing around with, because if this diverges, then anything larger will diverge. Okay, so here's how we do this. We'll take the easy step first. If I drop off the 2, when I compare n plus 2 into n is the smaller of the 2. So this step is not too bad. N plus 2 over square root of n cubed plus 4 is definitely greater than that. Okay. Now I need to make sure that this is greater than what I got when I dropped off the 4. Well, we're going to have to play around with it. If I just drop off the 4, I'm making my denominator smaller, which makes my whole fraction larger. I don't want to go larger, I want to go smaller. So here's the standard maneuver with this type of thing. I'm going to replace basically anything that's less than n cubed with n cubed, as long as it makes sense. Is it true that if I replace 4 by n cubed, I get something larger? Well, when n is large enough, yes, that's true. Okay, so I'm going to replace 4 by n cubed. Now in the denominator, I have n cubed plus n cubed, which gives me 2n cubed, but that's under the square root. I can pull off the 2 that's in the square root. We get 1 over radical 2 times n over the cube root of n, or the square root of n cubed, which reduces to this. Okay, so I know if I trail things back, my sequence is greater than this sequence. This sequence diverges, so that guy is going to diverge, or that series is going to diverge. So here we wrap it up. Since this series diverges, and since this, which is our sequence, is greater than the sequences or the series that diverged, by the comparison theorem we know that our series is going to diverge.